All right, so today's video, we're going to be talking about some imaginary roots. We're going to focus on imaginary, but I am going to start the process of helping you to determine how to find all of your roots, whether they're real rational, whether they're real irrational, whether they're imaginary. So we're just going to talk about the process. We're going to talk about where imaginary roots come from, and again, we'll build from there. So where do imaginary roots come from? Well, imaginary roots are going to come from the quadratic formula. And I'm not quite sure how many of you have dealt with the quadratic formula before. Some of you may have done it in Math 2. If you did not, it's definitely something to know, just because you're going to have a college class where you're going to have to do some old school methods, and most of the time that formula is what they're going to expect you to use. So it's x equals negative b plus or minus the square root of b squared minus 4ac, and that's all over 2a. All right, so looking at the quadratic formula, there's going to be three kind of general steps. I'm not going to go into details about them. I'm going to show you more than anything. The first step that you're going to do is you are going to look through Desmos for all of the real rational roots. So real rational roots are roots that can be turned into a fraction, whole numbers, that kind of stuff. We don't want any irrationals, because irrationals are going to be those square root numbers that are kind of like pi. They're going to just keep going on, and the decimals are never going to end. So then step 2 is once we find those real roots, we are going to reduce our polynomial. So we're going to use some synthetic division, or if you prefer to do long division, and we're going to reduce that polynomial. We want to reduce the polynomial with the real roots so that we can get a quadratic. Why? Because we want to use the quadratic formula. So once we reduce it down, we're going to use that quadratic formula, and that's going to give us our imaginary roots. Okay. So I'm going to show you an example. I kind of got a little tree map up here for us to organize some information, and we're going to do a couple of examples from there. So down here, I have x to the third power plus x squared plus 7x minus 9. So the first question that you're going to have is, how many total roots do I have? Well, my total roots is going to be from the fundamental theorem of algebra. Remember, that is the highest degree. So my highest degree in this problem is 3. So this is going to turn into a 3. We have 3 roots. I don't know how many of those are real. I don't know how many are imaginary, but we have 3 total. So then we kind of got to separate them. So remember, we start with the real roots, and we're going to start with the real roots. We're going to do that graphically through Desmos. So when I go to Desmos, I'm just going to plug in my actual quadratic that I've been given. And I'm going to look at where it crosses the x-axis. Remember, x-axis is going to give us real roots. But we want to be very careful to make sure we identify any multiplicities that may happen. So when I'm looking at this, I'm going to zoom out just a little bit. And I see that it doesn't come back to the x-axis, but I do see that it crosses one time at 1. Now, if it crosses the x-axis, it doesn't kiss it, or it doesn't have a point of inflection, that means it has 1 root. So we have 1 real root, and that 1 real root is actually at the value x equals 1. So we know that we have 1 solution at x equals 1. So that means that if I make it into a factor, this is going to be x minus 1. Because remember, when we take it in and out of that binomial, it's the opposite value. So what we want to do is we are now going to reduce our polynomial. We're going to use any real roots that we found, and we're going to reduce that polynomial using synthetic division. So we're going to take our original, and we are going to divide it by x minus 1. Okay, so I'm going to come down here, and I'm going to do some synthetic division here. So we know that our k value is equal to 1. And since the k value is equal to 1, we have the coefficients 1, 1, 7, negative 9. And we're going to do our synthetic division. So that's going to be 1, 2, 9, and we should get a remainder of 0. Remember, when we have a remainder of 0, that confirms to us that that is a factor, which we know it should be a factor because we just found it as a solution. So our reduced polynomial, so we just reduced that polynomial and we reduced it. So we started with x cubed. We now have x squared plus 2x plus 9. Now, with this polynomial, I could potentially try to factor it. I could try to find how many number or what numbers multiply to give me 9 but add to give me 2. But it's really going to be in vain because we're not going to be able to do that. I've already established that we don't have any more real roots. In order to factor, you have to have real roots. So there's no set of numbers, 1 and 9, that when added together can give me 2. So that's where the quadratic formula comes in. I now have an exponent of 2. So I'm now going to take that information and I'm going to plug it into my quadratic formula. Okay, so my quadratic formula, what do the A's, the B's, and the C's and all that come from? Well, all of my A's, my B's, my C's, they're going to come from ax squared plus bx plus c. That is the standard form of a quadratic. Now, the question is how many imaginary roots am I going to have? Well, think about your conjugate theorem. So the conjugate theorem says that we have imaginaries and irrational in sets. So if I need 3 total, and I have 3 total, I have 1 real, and I have a degree of 2 left over. So that means that I'm going to have 2 imaginary roots left in my problem. So when I When I factor this, I'm going to have 2 imaginary roots. And we're going to take that reduced polynomial, x squared plus 2x plus 7, and we are now going to plug that into our quadratic formula, okay? And that is going to produce our imaginary roots that we have. So the next thing I'm going to do is I'm going to identify what my A, my B, and my C are. So this is the problem we're looking at. And, oh, that should be a plus 9. That was my mistake. Okay, so my A value is equal to 1. My B value is equal to 2. And my C value is equal to 9. All right, so we're just going to take all of that information and we're going to plug it right into our problem. So I now have x equals negative b, so b is going to be 2, so negative 2 plus or minus the square root of 2 squared minus 4 times 1 times 9, and that's all going to be divided by 2 times 1. All right, so we're going to reduce this. And I have 2 squared minus 4 times 1 times 9. And that is going to give me 32. No, negative 32, sorry. So this is going to be x equals negative 2 plus or minus the square root of negative 32 over 2. So we've reduced this. But where does the imaginary come from? So remember, think back, that when we talked about imaginary numbers, we talked about imaginary numbers in the format that the square root of a negative 1 is I. And we're going to use that I now in this problem because we can't take the square root of negative 32. Okay? So what we're going to do is we're going to actually reduce that and we're going to pull out that I value in my problem. So I have x equals negative 2 plus or minus, and right here is where I'm going to put my I. That square root of a negative now makes it so that we can make this a positive square root of 32 and deal with it. Okay? And I just need to simplify this. So we're going to need to go through the process of simplifying our square root, and we're going to need to go through the process of simplifying the entire problem. So how do I simplify the square root of 32? So that's going to come from doing a factor tree. So if I have the square root of 32, that's going to give me 2 and 16. Well, 16 is a perfect square, so that is going to wind up equaling the square root of 16, which is going to be 4. So I now have x equals negative 2 plus or minus. Now I'm going to pull out 4, so 4i. And yes, you put the 4 in front because it's kind of like doing a variable. When we don't do x4, we do 4x. So we're going to do 4i square root, and we're going to leave that 2 inside because that wasn't a perfect square, divided by 2. All right, and the last step, we do need to simplify. But when you simplify, we've already simplified what's in the radical, the square root symbol. We need to simplify the outside. So to simplify the outside, all we're going to do here is we're going to divide -2 and 2 and 4 and 2. All right, so -2 divided by 2, that's going to turn into -1, plus minus. 4 divided by 2 is going to be 2i, and then the square root of 2 is left alone. So I now have 2 roots. I finally have a set, two imaginary solutions in my problem. I have x equals -1 plus 2i square root of 2, and I have x equals -1 minus 2i square root of 2. So I have 2 imaginary roots, and I have 1 real root that we found over here, that x equals 1, to give me a total of 3. So just again, let's kind of talk through this situation. I had a exponent, or excuse me, I had a polynomial, and its exponent had a degree of 3. So we knew we needed 3 roots total. We graphed it, and when we graphed it, we saw that we had a 1 real root at +1, and we took that +1 and we did synthetic division and reduced that polynomial down. We needed to reduce it down so we could get x squared and do the quadratic formula. So then we came over here and we did the quadratic formula. We plugged all of our information into the reduced polynomial, and we came up with 2 imaginaries. Okay, so given that, I was going to look at just another example, so you had a couple of examples to look at. All right, so with this particular problem, I'm just going to write this one out. So I have x to the 4th plus x to the 3rd minus 3x squared plus 8x plus 20. Okay, so the question is how many real roots or how many total roots do I have? So I have 4 total roots. So that means in the end, no matter how many imaginaries, no matter how many reals, we need 4 total. Okay. Now, the next question is how many are real roots? So how many real roots do we have? So we're going to graph that. So we're going to do y equals x to the 4th. And remember, real roots are where they're going to cross the x-axis, and we're always going to continue to look for multiplicity. And remember, even multiplicity is when it kisses the x-axis. Odd multiplicity is when it has a point of inflection. So I'm going to zoom out, make sure it doesn't come back to the axis anywhere. And I should see that it kisses the x-axis at -2. So I definitely have a real root at x equals -2. The question is what type of, or how many even multiplicities do I have? Do I have 2? Do I have 4? Do I have 6? Well, we can't have 6 for sure because we only have a total of 4. So the question is do I have 2 or do I have 4 multiplicity? Because remember, we established that even just means that it can have 2, 4, 6, 8, and so forth. So how do we figure that out? Well, we're going to do our reducing. We're going to do synthetic. As long as it equals, the remainder is equal to 0, it still has that many roots. If it stops equaling to 0, then it's done. All right, so I'm going to come over here and I'm going to do some synthetic. So my k value is -2. And I have 1, 1, -3, 8, and 20. All right, so 1, -1, -1 again, positive 2, 10, negative 20. So that did work because we got a remainder of 0, but we have multiplicity, so we need to do it again. So we're going to do k equals negative 2 one more time. Sorry about that. My daughter was coming in from outside. And then I have 1, negative 2, and I'm going to keep going through the process. So this is going to be positive 5, and this is negative 10. All right, so at this point I've reduced it down, but I need to at least try. So we know we have at least 2 roots of negative 2. Do I have more than negative 2? So do I have more than negative 2? Means I need to try and do synthetic division again. If it works, then I have 4 total. If it doesn't work, then I only have 2. All right, so I'm going to try it one more time. And I'm going to have 1, negative 2, negative 5, and 10. So we can see here that remainder does not work. So we are not going to wind up having division more than 2 times. So like just at that point, we now are done. We know that we have a total of 2 real roots. And I'm going to put a multiplicity of 2 here. Okay, so that has a multiplicity of 2. So now we've reduced this problem down. So we now have a quadratic, and my quadratic is x squared minus 3x plus 5. So we're going to do the quadratic formula, and with that quadratic formula, because I have 2 real roots, I should have 2 imaginary roots after this. All right, so I know that a is equal to 1, b is equal to negative 3, and c is equal to 5. All right, so x equals negative 3. And yes, that is a double negative because the formula is negative and the number is negative. And we're going to do plus or minus. And we're going to do negative 3 squared minus 4 times 1 times 5 all over 2 times 1. All right, so let's figure out what this inside piece is going to be. So we have negative 3 squared minus 4 times 1 times 5. That gives me negative 11. So negative, that's going to be positive 3. And we have negative 11 over 2. Okay. So we now realize that we are going to have imaginaries, or you should realize that we're going to have imaginaries based off the fact that I have a negative square root. So we're going to pull that negative, or pull that I out. So plus or minus, and we're going to put an I right here. And that's going to continue my problem and make that the square root of positive 11. Now, the great thing about it is 11 is a prime number, so we're not going to have to do a factor tree for 11 because there's nothing to factor. And our division, we can't take 2 and divide it into 3 without getting a decimal. So at this point, there's no more simplifying that we have to do. So my final 2 roots that are imaginary are 3 plus I square roots of 11 over 2 and 3 minus I square roots of 11 over 2. So I have a total of 4 roots. Those 4 roots, I have 2 imaginary, and I have 2 that are real, and their multiplicity evens. All right, I hope this helps. We are going to do some more of this once we go back again and talk about all real roots. We're going to do some more a video on practice examples and continue from there.